Hello everyone and welcome to our contemporary math lesson on 4.3. Today we're talking about other bases. Now let's look at two positional value systems to figure out how we deal with other bases. So we've already talked about the Hindu-Arabic positional values, and these were 1, 10, 10 squared, 10 cubed, 10 to the fourth, or 1, 10, 100,000, 10,000. We've also looked at the Babylonian positional values, and that was 1, 60, 60 squared, 60 cubed, 60 to the fourth. Okay, now the way it works is Hindu-Arabic is in base 10 and Babylonian is in base 60. Now it turns out that any counting number can be a base. So we can be in base 8 and we would have these positional values. So it would always be the ones column and then the eights column. And then it just continues on, 8 squared, 8 cubed, and 8 to the fourth. Okay, so this would be 1, 8, 64, 512, and 4096. So what this is telling us is that each number in a certain place value is worth these amounts. Go ahead and write out the base 2 positional values using the same pattern that we've seen here. So it's going to be 1, and then 2, then 2 squared, 2 cubed, and 2 to the fourth. So base 2 positional values will be 1, 2, 4, 8, 16, and so on and so forth. If we were talking base B now, we would start off with 1, and then the B, and then B squared, B cubed, B to the fourth, and so on. So this is how we take the base and determine our positional values. Now some other things that we're going to see, a number written in a base, let's just write a number here in base 8. So I could write the number like 3274 base 8. So you can see that the base is written down here. And then up here, no symbol can be the base or higher. So no symbol for 8 or higher. So when we think about this, we can count in base 8. We would count 1, 2, 3, 4, 5, 6, 7. Well, now we can't use what we know as the symbol for 8. We're going to have to rewrite this as 1, 0. So what that means is one group of 8 with 0 left over. And then for our next one, we would write 1, 1. So that's one group of 8 with 1 left over. So that's 8 plus 1 is 9. And then it would follow our same pattern here. We have to avoid the temptation to say 12, 13, 14, 15, 16, and 17. This is 1, 2, base 8, 1, 3, base 8, 1, 4, base 8. So this one right here would be 1, 7, base 8, which means one group of 8 with 7 left over. And that is what we would think of as the number 15. So again, we can't go up to 1, 8 now, so we would have to go to 2, 0. So we're saying two groups of 8 with 0 left over, and we would continue counting just the same way. Alright, so we want to be able to convert some of these numbers back to base 10, or our normal HA Hindu-Arabic numerals. So here's the number 234 base 6. So what I like to do is just spread this number out a little bit. And I'll just write 2, 3, 4 right here. And then I'll make a little chart here to help me stay organized. So I write the number on the top, and then I write the corresponding place values down below. Okay, so all the way to the right is always a 1. Then we use the base of 6, and then we would use 6 squared, or 36. Then to find our answer, we actually make this into a multiplication problem, and we go 2 times 36 is 72, 3 times 6 is 18, and 4 times 1 is 4. So again, when we think about our place value systems, we would say we have 4 ones, we have 3 groups of 6 each, and 2 groups of 36 each. So if we were to add this together now, we would get 94. Okay, so what we're really saying is 2 groups of 36 and 3 groups of 6 and 4 groups of 1 is the same as 9 groups of 10 and 4 groups of 1. Let's try another one here. Okay, so again, I write out my number, 3, 6, 1, 5. Then I'm just going to separate it out by place values. And then I'm going to write the place values of base 8. So it's going to be 1, 8, 8 squared, which was 64, and 8 cubed, which was 512. Okay, so again, if you forget how to do these, you just look at your base and remember how we came up with these. 1, 8, 8 squared, 8 cubed, so on and so forth. Okay, so now this whole thing becomes a multiplication problem. It's going to be 3 times 512 plus 6 times 64 plus 1 times 8 plus 5 times 1. And this is the number written out in expanded form. So we'll just do this in our calculator now. 3 times 512 plus 6 times 64 plus 1 times 8 plus 5 times 1. And so our total here is 1,933. And that would be the final answer. Let's take a look at the next one together here. This is in a base 2 system, and we also call this binary. And it's actually the code that all computers use to do all of their computing. Okay, and it actually corresponds with the bits that we're able to produce. And what I mean by the bits is if we look at our place value, we're going to see it's 1, 2, 2 squared, which is 4, and then 2 cubed, which is 8, and then 2 to the 4th, which is 16, and then 2 to the 5th, which is 32, and 2 to the 6th, which is 64. So what it means for something to be 64-bit, it means all of the numbers can have 1, 2, 3, 4, 5, 6, 7 digits in them. Okay, so all these combinations are available in a 64-bit type of system. So if we're going to translate this number now into base 10, let's just go ahead and write out our number first. And then below it, we're going to write out the place values here. So we'll make a little table. And we always start at the right, and then we're just going to write out these place values here. So it's worth 1, 2, 4, 8, 16, and 32. Now this number gets very long because it can only be a 1 or a 0. Those are only digits because we are in a base 2. But what that does for us is translating this number becomes very simple because you're either multiplying by a 1 or by a 0. Okay, so this becomes a fairly simple. It's 32. Here we have 0 16s, we have 1 8, 1 4, 0 2s, and 1 1. And so let's go ahead and add this up. So we have 44 and actually 45 is our number. So you might be starting to see how this is working. The higher the base, the more compact the number because you have more digits more numerals represented. The lower the base, the more spread out the number, but a lot less complex. Okay, I want you to try example 4 on your own. Go ahead and pause the video, come on back when you're done. Alright, welcome back. So here we have 30421 and we are in base 5. So below it you should have written out the place values for base 5. So 1, 5, 5 squared, 5 cubed, and 5 to the 4th. Then you should have multiplied each of those and added them all up, and you should have come up with 1986 or 1986. Next we want to talk about bases that are higher than 10. And when we do this, we have to use letters to represent the numbers. So in base 12, we're always going to let t equal 10 and e equal 11. So let's count in base 12. Okay, well we would do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so remember, t replaces the 10, e replaces the 11. Now if we wanted to write 12, we would actually write 1, 0. And this would be base 12, of course. If we wanted to write 13, we would write 1, 1. 14 would be 1, 2. So one thing to notice is whatever base you're in, it's always going to be 1, 0, and then the base. So let's convert this 1, 2, T6 base 12 into base 10. So we're going to write our number 1, 2, T6. We're going to put this into base 10. So we need the place values for base 12. So it's going to be 1, 12, 12 squared, which is 144, and then 12 cubed. Well, 12 cubed is going to be 12 times 12 times 12. So it's 1,728. So looking at this number, we have 1,728 plus 288 plus. Now this T12 we think of as 10 times 12, which is 120, and then plus 6 times 1. So let's go ahead and add all these up. 1728 plus 288 plus 120 plus 6, and our total is 2,142. So you can see here, since base 12 is higher than base 10, our number gets more compact, and you can see it's lower than our base 10 number. Now we also have something called base 16, which is a very common system as well. This is called a hexadecimal system, standing for 16. Now in this case, once we get past 9, to represent 10 we use the letter A. For 11 we use B, 12 we use C, 13 we use D, 14 we use E, and 15 we use F. So if we were counting in base 16, we would just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 would be F. And how do we write 16? 1, 0, base 16. So go ahead and try to convert 5F19B base 16 into base 10. Go ahead and pause the video and come on back when you're done. Alright, welcome back. So you should have written out your number here, 5F19B, and then you should have written your place values. So we have 1, 16, 16 squared, 16 cubed, and 16 to the 4th. Then you should multiply and add together. So I like seeing it in an expanded form because it shows us that we have 5 groups of 65,536 plus 15 groups of 4,096. And you'll recall that it was 15 because it was the letter F, and F equals 15. And then 1 group of 256, 9 group of 16, and then B was 11 right here. So it's 11 groups of 1. When you add all this up, you get 389,531. So that's been converting a number in a different base to a number in base 10.